All right, welcome back. So we just discussed, of course, Cebeci-Smith before, and I had the limitation of estimating boundary layer parameters, and Baldwin-Lomax, which is Computer Project 4 model, overcame those, and it worked really well for certain types of flows, but it really had trouble near points of large gradients and large changes, turbulent flows that are far away from equilibrium. And to overcome that, people started thinking, well, I need to use models with additional differential equations, preferably partial differential equations, like in the one equation, two equation, and higher order or higher number of equation models. But those are very expensive to use, sometimes even today. And so maybe there's something in between. And this is where one of the first differential equation models came in. And it's not called the one equation model. The turbulence community, sort of identified and adopted a name. Maybe it's a little bit of slang. You might say it's a 1/3 or 2/3 model. Nope, they chose 1/2. And in the paper, Johnson and King actually denoted why they viewed it as a 1/2 model. And they said it's a half model because it denotes that an ODE, ordinary differential equation, for the Reynolds shear stress, actually the maximum value in the whole boundary layer, is used rather than a partial differential equation. So I suppose the view is that like a one equation or two equation model for closure actually are additional partial differential equations is one way to look at it. But this is one idea where instead of, say, tracking one-point statistics along the boundary layer, they created an ODE to track the Reynolds stress at some intermediate through the region through the boundary layer. So there's a boundary layer, and there's some line of maximum Reynolds stress. That there's some ODE that tracks its evolution along that line in the boundary layer. And they would just assume that it's roughly at some distance from the wall and it's relatively parallel to the wall. And that worked really well. Who are the people who created this model? Dennis Johnson, I don't know much about him. I looked online some and I sent an email to a few friends and I haven't heard back yet. The second author was Lyndall King, and he got his graduate work, Ph.D.s, through Stanford Aeronautics and Astronautics, and then he became a research scientist at NASA Ames Research Center for 37 years, working in the same CFD group. And so this is all from his obituary. He just actually passed away 4 years ago in 2018. That's too bad. That's him enjoying retirement, looks like. And so let's look at what they did. And they call this, in 1985, a few years after the Baldwin-Lomax model, a non-equilibrium algebraic model. It's the half equation model. And why is it non-equilibrium? Because they're going to modify the closures of Cebeci-Smith and Baldwin-Lomax to try and estimate turbulent eddy viscosity when the turbulence is no longer in equilibrium. And they're also going to add in a single differential equation that tracks one quantity, the off-diagonal Reynolds stress term in the turbulent boundary layer. So that's the idea. And a few big notes is that it's an ODE model, one ODE for, say, UM, which is going to go as U prime, V prime. And this will be much more clear when we bring up the actual article, which I passed out. And of course, it's an ODE, not a PDE. And you'll see pretty much all the other models we're going to look at this semester for RANS closures are PDEs. And it's really the community that's adopted this funny notation. And there really aren't many half equation models. And it was really pioneered by a Stanford turbulence prediction workshop. And it's sort of like a little Olympics where all the CFD groups and turbulence modeling groups came in and they applied their CFD codes to tons of different flows and they see how everybody did on the same experiments. And from these types of workshops, they actually identify ways to go forward. What are the problems? And they do these things today in all kinds of different fields, like through AIAA. Like there's a very popular drag prediction workshop. They use, and you'll see this in the paper, but just to really show you the major equations, they use like a blended equilibrium algebraic model that might go as mu t naught times hyperbolic tangent of mu ti over mu t naught. And T naught and Ti are the inner and outer eddy viscosity. This is hyperbolic tangent, excuse me. And so this is just a blending factor. So before they were looking for immediate locations, they're using a blending factor. It's also a two-layer formulation. Here's a summary of the inner layer. So there's eddy viscosity in the inner layer. You should recognize terms like this from before, and they're adding on little extra terms. Usually this y appears over on this side, like in the previous model. So is this coefficient k. What you'll notice here, in particular that's really useful, besides these length scales, is this quantity um. And um is going to be tracked by the ODE. So not only are you solving continuity, momentum, and energy in the boundary layer equations, you're also solving an extra half equation, which they call the ODE. Here, um is like a scale. To model and capture turbulence statistics outside of eddy viscosity. And I'll show you this form, which is from Wilcox, in a second. And also there's other scales, US and UD, to capture separation. So to make this model, there's a lot of empirical functions and terms that were chosen based on physical intuition and matching measurement data to get this to work. Okay. In the outer layer, there's a non-equilibrium model for the outer layer, and they introduce what they call a non-equilibrium parameter, sigma x, and that's just attached to the outer layer formulation. So all this is almost exactly, if not exactly, like the previous models, and they attach this extra term. And we'll look at that, how that's modeled in the journal article in a second. And then here, beyond all that standard algebraic modeling plus a few little modifications, this is their one form, at least, of their ODE, the one that's kind of written down in theory. And you'll see they simplified it for the actual solvers when we look in the paper. So this is what we call we're solving for and this is just like a lot of the equations we develop for turbulent kinetic energy. It can be derived that way. This is like a relaxation term, and this is what they call the turbulent diffusion term. So in a way, this is going to convect this Reynolds stress through the boundary layer along a particular line, not like in the whole field. And it's nonlinear, of course. Here's squared again, and cubed. So it's not too easy to solve numerically. Okay, so these are the major equations, and then here's the closed coefficients, which are similar to other ones we've seen before. For example, K, 0.41 typically. So let's spend a little less time looking at these notes and the overview major model equations and look at the actual paper, because I think it's more instructive. So here's the original paper of Johnson and King, NASA Ames Research Center, Moffett Field, California. Also an AIAA conference paper, and I think this was published in Aerosciences meeting. So this is the same conference as the previous paper, just about 6 years later, roughly. Reno, Nevada. They always used to be held in Reno. Okay, So I always think it's good to read the abstract, and I sent these in advance, so please just look at least the figures in advance. And right away they say what they do that's new. New turbulence closure model that's going to treat and attack the two-dimensional boundary layer problems with strong adverse pressure gradients. And here they say something really important. They talk about the history effects. And in the previous model, there's what we really call a lack of history. That what's happening in the upstream direction is going to really alter things going downstream. They're coupled through an ODE that's tracking this history of turbulence and try and capture things that are happening non-incrementally, like shocks and walls. And they note that they're introducing this ordinary differential equation, which is coming from the turbulent kinetic energy equation. So remember earlier in the class, we spent a lot of time developing the turbulent kinetic energy equation. So in their developmental papers, they took that equation and tried to reduce it to one single equation just for the Reynolds stress term UV. Okay, and in here they also mentioned that it has only a little bit larger CPU requirements relative to other models, which is important. So only a slightly more computational effort. So this is the criticism. By having a higher predictive capability, and it's often good to capture non-equilibrium effects for these flows, they have a higher computational cost than Cebeci-Smith and Baldwin-Lomax, which are just purely algebraic models, right? So you're introducing a whole new differential equation, and you got to pay for it. Okay, so let's look at a few key things. They're looking for prediction of airfoils up to and beyond stall in boundary layers using finite difference viscous codes. And key things. There appears to be capable of treating two-dimensional subsonic pressure-driven flows which are transonic, shock-inducing, and separated. So you see this is a case where Baldwin-Lomax failed. And in this paragraph, I thought was very interesting. They're talking about trying to find and model the history, the so-called history or memory of turbulence. And they do that through an additional ODE. And in here, they say exactly why they have a half equation solver. And they write the half is used to denote that an ODE for the Reynolds stress is used rather than a partial differential equation. Of course, having a PDE is much cheaper to evaluate than a full, PDE. An ODE is cheaper. And they lay out their whole benchmarking of this code in this NASA technical memorandum. Johnson and King, new turbulence closure approach for turbulent boundary layers with separation. And you can look that up today on ntrs.nasa.gov, free publication, courtesy of your tax dollars. And the Cebeci-Smith model was the model to beat. So they took a large number of experiments inspired by the Stanford turbulence benchmarking workshop for prediction, and try to overcome these non-equilibrium type flows and benchmark them against sort of the industry standard, which was Cebeci-Smith. And then also there was a rise of two equation models like K epsilon and K omega, which we'll talk about in this class, at least the major popular ones. And they say that their model might be more beneficial because a lot of people are spending a lot more computer power to evaluate models with more PDEs, like two equation models, and they're still finding equivalent predictions. And this is something people struggle with today, of how much fidelity in the model you want to have to find good predictions. So this is really a philosophical paragraph of why they're choosing to go with the simpler approach, because it's less costly. Some of this is philosophy too, which I liked. They said that their goal was to develop an adequate closure model for limited class of flows rather than a universal model. And a lot of people have been looking for sort of RANS closures that work for all flows, and even today we're failing at that. So maybe a lesson is, over the last 50 years, is it's good to try and create a prediction model for a classification of flows that runs fast and is accurate than trying to do something that sort of a jack of all trades and master of none. And here he talks about the Cebeci-Smith model and sort of some of its limitations. And it depends on delta and delta star or shape factors or something similar. And this model, like the Baldwin-Lomax model, has already overcome that. And almost all models had after these. And in their model, what really drove the work and probably got their time funded was this sort of statement here. It was postulated that a proper accounting for the convective effects was essential with diffraction effects in the flows. And in here, they want to focus on the streamwise direction of this quantity U prime V prime at M. Now, M is that intermediate location. So that's the location where the maximum Reynolds stress will occur in the boundary layer at any streamwise location. And we can maybe draw that here quick. Once again, you have your boundary layer, and you have sort of maybe some line through it. This is the edge. Here's your profile. Here's a location M, and along there's the ODE for U prime V prime bar. That was their core idea. And they had to form that ODE. And before they did that, they made three major improvements to previous models. So they, like I said, they have an inner model, and they have this blending factor. So that's the inner and outer eddy viscosities. Here's the inner one. And they wrote the inner eddy viscosity as a function of the Reynolds stress term to link it in with the ODE. And they have an outer eddy viscosity, which they made really simple, as an intermittency factor times a constant. So they lumped in all these constants and just made it really simple. And now they say, well, okay, we need some model to connect the inner and outer eddy viscosities, and this is where they did a little dimensional analysis. They said, okay, we're going to just model the eddy viscosity as going as the Reynolds stress, negative component, divided by partial U partial Y. And why did they do that? Because they're going to get units of something like, and they break this out, this is half, right? So multiply these together, we're getting the value. We'll get something like meters per second, a velocity scale, and meters. That's why this isn't really a denominator for dimensional analysis. Problem with this, of course, is you might say, well, partial U partial Y might become 0 as I get to the outside of the boundary layer, and if I go outside the boundary layer, that should become very small. The other side of it is that the Reynolds stress might also become very small. Well, it turns out typically your Reynolds stress is becoming smaller than your derivative, so this should remain small. But still, that term can go to 0. So you already see that there has to be some empirical factor in there to never let eddy viscosity become negative or 0. Well, excuse me, never really become negative. You want it to become negative. That wouldn't make any sense. Especially you wouldn't want this to be 0 and have this be positive, because then your code's going to blow up. And so you would have like a check. You would have maximum eddy viscosities and minimums in a practical code. Anyway, this is just a sort of a dimensional analysis and argument, and this is where they describe it. You can read that if you want. But this is now a model, and they need to track eddy viscosity at this location M with a differential equation. And this idea was actually put down by someone named Bradshaw many years ago. And if you take your Reynolds stress equation and you write it for one component, the U prime V prime component, and you say it's only valid along a line, and you apply the boundary layer approximations, plus one component, you get this wonderful transport equation. We have a convection term, a production term, a diffusion term, and a dissipation term. This is dissipation of basically this Reynolds stress component, not of the whole turbulent kinetic energy. So what do you have in here? You have Reynolds stress this is really turbulent kinetic energy at location M, and you need a way to relate Km and say U prime V prime, for instance, and also P prime V prime, and that's sort of some approximations they're going to make in this model. And I outlined one down here. And you can see that's a huge assumption in itself. They say negative U prime V prime bar over Km. So that's the ratio of this Reynolds stress component divided by the total turbulent kinetic energy is just a constant. Well, if I take measurements of high-speed turbulent boundary layers and plot U prime, or U prime, V prime relative to Y, their ratios are actually changing, especially for higher speed flows. But you might say for some of these boundary layers, that's going to be on the order of a small value, between 0 and 1, of course. You would never want it to be larger than 1. So you see, they take these kinds of approximations and put them back in for K so they can isolate all these terms in terms of U prime, V prime. And in the transport equation. And that's what they found in equation 6. So now see all our terms are U prime, V prime. Same types of terms. We have a production type terms here and transport. So they want to basically simplify this further, and you can see some of these like little relations they use to relate, say, dissipation U prime, V prime. They used like a length scale, and that's what this length scale LM is. So they have a new length scale, and they created simplified models for length scale here. So you can see this is a lot of work on their part to do all this. They took all this analysis and put it in for their eddy viscosity definitions, 2, 3, 4. And they get 8A, 8B, 8C. And then to solve all these equations, they introduced a transform to make it easier to solve. And that's G equals negative U prime V prime. So then you get equation 11. And this is the equation that's actually going into the code. So there's really this unknown term G, which they can relate back to U prime V prime, which goes back into their eddy viscosity models. So I'm just trying to hit the big picture of how this all works so you can get an idea of it. The bottom line is that there's a few major contributions, right? So they say there's one equation which is tracking Reynolds stress, which is from Reynolds stress equation for U prime V prime. They made a bunch of approximations to relate U prime and V prime to all the other terms, and then they relate the eddy viscosity to those terms. And of course, this took years of work, many computations on a lot of computers, and then they calibrated the coefficients against experiments. Then one of the big problems with all this is like, okay, well, you've introduced a new field variable that I need to predict, which is U prime V prime. So usually in these codes, I need to say, okay, the eddy viscosity is 0 or a small value, and I know the incoming velocity like U bar. And I start my prediction, just like you did in computer project 2 and 3, which you're working on. But now I have another unknown statistical quantity, which is U prime V prime, at the inlet condition of my flow. And that's a new problem. So there's a few ways to handle that. You can guess what it is, which isn't very satisfactory. You can use a measurement, which I may not always have. Or option 3 is to use another CFD code or model to estimate it. So you'll see this is one of the first cases where, and I've run in this problem in my career, where you have a new turbulence model, but to start it and get a solution, you actually need a solution from something else. So a great example is a modern model is called the K-epsilon-Chien model, which is in many popular codes. And I was told that if I wanted to use the model and get predictions, then I would have to solve the flow with another turbulence model and restart it, like use the initial condition and boundary conditions from a solution of another model. And that made me very unhappy. And this is exactly what's happened here. Initial conditions are needed in addition to the mean streamline velocity, and a value for U prime V prime is needed to start the calculation. And I read that, I really felt a little bit bad about the whole thing because it's a major setback in the model. Nonetheless, today you would also need to estimate, say, k epsilon or k omega in like a typical general CFD code. So one thing about computer times, VAX 1170s, we're running these simulations in about 2 minutes, which is wonderful. And so these are computers around the early 80s, which is a lot faster than the 30-minute time slots for Cebeci-Smith, and it's a more complicated model. So let's look at some of the results in the closing minutes of our class. And here's the first interesting flow field. And I was actually on LinkedIn yesterday, and someone showed on their page, a researcher, pictures from this experiment. And in wind tunnels, they basically put on an oil film and take pictures so they can try and visualize where shocks and separation are happening. And so these experiments were being done in the 70s and 80s, and they're still being done today, because it's a hard problem. And what you're seeing is a Mach 0.875 flow over basically what amounts to a transonic bump. And in your wind tunnel, the walls might be here, but farther away, of course, to minimize blockage. And they put a rod down the wind tunnel, like that. And they're going to have windows here to look in and take measurements of oil film flows, and they'll have pressure points on the body. And in a transonic flow, this makes the flow become supersonic through a local minimal area change between the wall of the tunnel and the body, right? So you've shocked the flow at this location, it's supersonic, and greater than 1 here, and there's a shock transonic form and a separation bubble behind it, much like you see on an airfoil in the transonic regime. So this is much more controlled, and it's axisymmetric, which is nice. The advantage of axisymmetric flows like this too is you can solve your axisymmetric form of the equations. So here's your basic schematic of that. This is x over c, something like this way, 0 x over c, and there. There's the measurements, shock location, and just to get an idea of what the measurements look like. Okay, so here's your shock-induced separated flow. And in all these experiments, they are very consistent. They had the experiment as the point. NTM is new turbulence model. That's the one we're looking at in the paper of Johnson and King. And CBSM, of course, is Cebeci-Smith's model. So they have the sort of industrial workhorse. They got the experiments, and they're their new model. And let's look at what they did by having a single ODE that tracks Reynolds stress at the location of maximum Reynolds stress in the boundary layer. Here's the x over c location, so that's right in here. This is 0, this is 0.5, this is about 1. And you can see the experiments are dots. Cebeci-Smith has way under prediction of coefficient of pressure on the body. And so this would be a shock location. And you see, because they've done it properly in our aerospace engineers, they made CP go negative in the positive direction, which is typical for airfoils in these types of experiments. So there's a shock. You know it's a shock because pressure is increasing, right? So it's a huge improvement in prediction that turbulence near the shock and separation is in non-equilibrium, and the inclusion of a single ODE in their code to track it with tons of empirical functions, which are fully explained in their NASA TM document, has greatly increased their predictive capability for a flow that all the other models couldn't before. So this is a great argument of always needing more than like 1-point statistics to describe the turbulence in your models. So let's look at one of their, this is shape factor, that's improved, okay. Let's look at some other flows. Shock-induced separation flow, Mach 8.75. So here's the velocity comparisons. 0.75 is 1. Oops. What happened there? Sorry. Yep. 0.75, 0.83, 0.875, 98, and then just past the end of the device. So this is the location E right there, 0 to 1. Okay, so this is at 0.75. negative. Oh, they're red on there. I don't have to label them. Okay, well, that's cool. Solid lines are the new predictive model. Dashed line Cebeci-Smith. Experiments are dots. And this is distance from the wall in centimeters, as you can see. And then this is a velocity, of course, normalized. So in all these cases, it looks like they're generally better predictive, but not always. I suppose near the wall, they have a bit of an inflection that's not captured as well. Anyway, it just gives you an idea. Here's another experiment which I thought is interesting. This is a diffuser. Another famous experiment. People like the benchmark again. Here's the x direction, flow left to right. The upper wall is curved, and with an incoming subsonic flow there, your flow is going to slow down and then speed up as your contraction gets bigger and smaller through here. And that's shown kind of like through this boundary layer at the wall. And what happens here, you can see here at the wall, because of this diffuser, the flow is actually separating. And you can see here's the zero velocity, so you actually have a negative velocity at the wall, and you have a positive velocity away from the wall, and this dashed line here is the edge of the boundary layer. So you see this simple subsonic flow with turbulent boundary layer has separated because of basically the induced pressure gradient of the diffuser. Huh. Well, that's not good at all. So, just a few more minutes, we'll just look at these. Once again, they tested their new turbulence model against Cebeci-Smith, and there's no turbulence measurements of U prime, V prime, but there are some measurements of boundary layer thickness. So they don't have necessarily one-to-one measurements. But down in here, you can see here's the pressure point measurements on the diffuser in the downstream direction. And especially downstream in region of separation, there's a big difference between Cebeci-Smith and the Johnson-King model. Matches experiment. Looks pretty good. And those are diffusers. Let's see if there's, these are, yep, more diffuser flows. Okay, one more flow. This is a transonic supercritical airfoil. Let's just do this last one. And these are measurements of displacement thickness with chord. So there's the chord. This is 0 and 1. Angle of attack, 4.32 degrees, and Mach 0.72. It's a supercritical airfoil. Why? What's a supercritical airfoil again? Nobody remembers? So they're designed by Richard Whitcomb originally at Langley to reduce the onset of transonic drag. Anybody flying a commercial aircraft in the last 5 years? Okay, so they all use the concept of supercritical airfoils, right? That way you can fly at higher Mach numbers and reduce the onset of transonic drag. So that's why they have this funny shape. And you can read all about that if you want. I talk about them briefly in my compressible flow class. Anyway, with higher Mach numbers, you should have shock formation occur at higher Mach numbers relative to an equivalent airfoil. Let's just look at some of the experiments in the two turbulence models just really quickly. This is the shock location. So this probably happens on the airfoil, of course, at the suction or pressure side. Hopefully shocks occur on the pressure or lower side because it increases lift, right? And I wouldn't want shocks on the upper side. So generally the two codes are in agreement except for nearly the trailing edge. Shape factors are in general agreement. And here's the boundary layer profile. So you can see in these cases, once again, their model has slightly better improvement, especially for the downstream locations where you have separation due to shocks, which is part of the whole reason they created the model. So it's predictive. Okay, with that, I just wanted to summarize everything. I think those are the algebraic models I wanted to talk about. And on Thursday, what we're going to do is just look at the basis for one equation models. And pretty much every CFD code, commercial CFD code, you can get like Star or Fluent or other models. They have multiple one equation models to choose from, and that's where we're going to go. Okay, so thank you for your time. See you Thursday.